Hey everybody, welcome to the 12.6 notes. I'm going to combine two lessons into one in this video. I'm going to do surface area and volume. I previously did surface area in one video and volume in another set of notes. So I have everything solved out ahead of time to hopefully save time, and I will just kind of explain as I go through them. So to start off with, we're going to talk about the surface area of a sphere. The surface area of a sphere formula is just 4 pi r squared. And I will talk more about this when we get to an example, but the surface area of a hemisphere is 3 pi r squared. But let's go back and talk about this 4 pi r squared. So the surface area of a sphere, that's just the outside of the sphere. It's 4 pi r squared because if you take a circle, like a two-dimensional circle, and you try and fold it like over a ball, that circle being like the circle that goes through the middle has to be the right size circle. But anyway, if you take it and you fold it over like a ball, it would take 4 of those circles to cover up that sphere. So that's how we have the formula of 4 pi r squared. So anyway, if you have a radius of 6, do 4 pi 6 squared, that's 144 pi, and that's about 452.39. Round to whatever decimal place your teacher asks of you. And these examples, I'm going to round to the nearest hundredths. This one, the picture is a little confusing. It's got a line all the way through, so I'm going to gather that this is the diameter. So therefore, my radius is going to be 11 feet. So I'm going to do 4 pi times 11 squared. Next, we have a little bit of vocabulary. A plane can intersect a sphere in a point or in a circle. So if you place a sphere like a ball on a tabletop, they are intersecting at a point. But once that plane goes into the sphere, then you are creating circles. And so if the circle contains the center of the sphere, the intersection is called a great circle. So it's basically the circle that goes right through the middle of that sphere. The endpoints of a diameter of a great circle are called poles. Okay, so the poles are labeled here and here. We don't talk too much about poles, but we will talk about the great circle in these examples. Because if you were to just cut off a sphere at the great circle, then you would create a hemisphere. So it says, since a great circle has the same center as the sphere and its radii are also radii of the sphere, it is the largest circle that can be drawn on a sphere. A great circle separates a sphere into 2 congruent halves called hemispheres. So if I'm going to find the surface area of the hemisphere, I am going to do 3 pi r squared. And you might be thinking, why aren't we doing 2 pi r squared? Because a hemisphere is half a sphere, and the surface area for a sphere is 4 pi r squared. So I can explain it to you like this. If you were to cut a sphere in half, it would create it would give it a bottom of that sphere, right? Otherwise, you'd have like this empty sphere, like a contact lens, and it would have no bottom. So you have to account for the bottom face of this sphere. And so when you cut a sphere in half, yeah, you would divide it by 2. But now you have a bottom circle, like a bottom surface, that you didn't have before when it was a whole sphere. So because you have a bottom circle or bottom surface, you have to add in the area of a circle, which is just pi r squared. So you're cutting this in half. This would make 2 pi r squared, and then you're adding in the area of that bottom now, which is pi r squared, and that makes 3 pi r squared. Okay, so hopefully that makes sense. So again, just imagine if you cut a sphere in half and it doesn't have a bottom, picture a contact lens. But if it does have a bottom, like if you cut a ball in half, then you have like a bouncy ball. Then you have a hemisphere, like a proper hemisphere, I guess, with a circle on its bottom. So anyway, I'm going to plug in 2.8 into 3 pi r squared, And that got me 23.52 pi, which rounds to 73.89 square centimeters. Make sure you always square your units when you're doing surface area. Just think the radius is being squared, so your unit should be squared. That kind of helps me remember whether it should be squared or not squared or whatever. So this one, it is giving me the circumference, and this is the great circle, meaning the circle that goes through the middle of the sphere. So I have to use this to figure out what my radius is. Well, the formula for my circumference is 2 pi r, so just set 5 pi equal to 2 pi r. So I can divide 2 pi to the other side. My pi's would cancel, and 5 divided by 2 is 2.5. So I have a radius of 2.5. Plug that into your surface area of a sphere formula. 4 pi times 2.5 squared gets me 25 pi, which is about 78.54 square meters. On this next example, I'm going to find the surface area of the sphere, but instead of giving you the circumference of the great circle, I'm going to give you the area of the great circle. So you got to go back and think of your area formula. Your area for a circle is pi r squared, so area was given to me as 220. So set 220 equal to pi r squared. So therefore I can divide pi to the other side, and that'll leave behind r squared. And so now I'm going to have to get rid of the power of 2, and I can do that by square rooting both sides. And I'll leave my radius as the square root of 220 over pi. The reason why you want to do that is because it's going to give you a decimal that goes on forever, and you don't want to have to round that number because you need to plug that number into your surface area formula. So if you can keep it in the non-rounded form, which is the square root of 220 over pi, then you can get a more accurate answer. And so when I do that, I actually get 880 exactly, because the formula says do r squared, and so if you square a square root, they cancel each other out, and so you have 4 pi times 220 divided by pi, so your pi's would actually cancel out, and you're just essentially doing 4 times 220, which is 880. So if you had rounded that earlier value, you would not have gotten 880. So this next example is a composite figure, and it's almost like, just imagine it kind of like a rounded bullet, and so it's basically a hemisphere on top of a cylinder. And it's very interesting because you're talking about surface area, right? And surface area is everything you can touch. So if you think about a hemisphere, it would normally have a bottom of the hemisphere that you could touch, and a cylinder would have a top and a bottom that you could touch. But the top circle of the cylinder is part of this hemisphere, and the bottom circle of this hemisphere is part of this cylinder. So what I'm trying to get at is you need to remove the area of the circle from your hemisphere, and you need to remove the area of one of your circles from your cylinder because they are touching. You can only touch this upper part of the hemisphere and the bottom part of the cylinder, if you will. So I hope that makes sense. I did put this note right there. Maybe you want to pause the video and read it yourself, but I essentially just explained that. So here I have my surface area of my hemisphere without the bottom circle, because it would be 3 pi r squared, but it's going to be 2 pi r squared because you don't have that bottom circle because it's touching the cylinder. And then your surface area of your cylinder would be 2 pi rh plus 2 pi r squared, except that second circle is part of that hemisphere, and so you got to remove the 2 and change it to a 1, or just take the 2 out. And then you're just plugging in 6 for your radius and 4 for your height, and doing all that gets me 156 pi, and then that's going to round to 490.088 square centimeters. Next to it, it's actually pretty similar. You have a hemisphere going inside of a cylinder, like you scooped it out. And so since surface area is something you can touch the inside of that cylinder now. So you could kind of imagine this cylinder, you could kind of technically remove that hemisphere and pop it out, and it would look like this picture right there, because we're talking about surface area. If you were to pop it out, you'd be touching this part of it that's now out. I don't know if that helps anybody's mental picture or makes it worse. If it makes it worse, then just forget I said anything. But essentially, you're going to have to remove the surface area of one of the bases, that's a circle, from your cylinder because of the carved out hemisphere. This top is supposed to be empty. Then you need to add in the surface area of a hemisphere without the area of a circle in it because, again, this top is empty. So your formula would look like this. I would take the 2 out of my surface area of my cylinder, the 2 from the 2 pi r squared, because you don't have 2 circular bases, you only have 1 circular base. And then instead of doing 3 pi r squared, I would do 2 pi r squared because, again, I don't have the circle attached to that hemisphere. And so if I were to add this all up, I'd have a pi r squared and a 2 pi r squared. That would essentially just combine to make 3 pi r squared. So my surface area of this combined figure would be 2 pi rh plus 3 pi r squared. And you would just plug in 3 for your radius and 9 for your height. And so it would look like that when you plug in all those numbers. And basically you would get 81 pi, which is approximately 254.469 cubic inches. So I didn't spend any time really talking about, I'm going to plug in a 6 there or 4 there, because if you know that 3 is your radius, I'm going to gather you're going to plug it in every time you see an R. And if you know 9 is your height, you're going to plug it in every time you see an H. The hard part about these is figuring out exactly how to change your formulas to adjust for how the shape has changed. Last thing to talk about is the volume of a sphere. So volume is the amount of space that your shape occupies, like on the inside, right? So your inner volume, of a sphere is 4/3 pi r cubed. So since you're cubing your radius, all your units will be in cubic units, like cubic centimeters or cubic inches or whatever. And so if you cut it in half, it's just half of your sphere, so it's just 2/3 pi r cubed. Nothing special about the volume of a hemisphere formula because we're talking about all the space that is inside of it. So that's why you can just get away with just purely cutting in half the volume of a sphere formula. So I just cut in half that top number to make the 2/3 pi r cubed. So here I have a hemisphere with a radius of 6, so just plug in 6 to 2/3 pi r cubed, and 2/3 times 6 cubed would make 144. Times it by pi, you'll get approximately 452.389 cubic meters. The next example, I have a circumference of the great circle as 18 pi. So my circumference formula again is 2 pi r. So I'm going to set 18 pi equal to 2 pi r. I'll divide 2 pi to both sides, and my pi's would cancel. So 18 divided by 2 is my radius, which is 9 centimeters. Then plug in 9 centimeters into your volume formula. So 4/3 times pi times 9 cubed would give me 972 pi, which rounds to 3,053.628 cubic centimeters. Okay, so for my final example, I'm going to give you the volume and we're going to work backwards to figure out the radius. So basically, you just take what they give you for the volume and set it equal to your volume formula, which is 4/3 pi r cubed. And so your radius is your only variable, so divide out your non-variable terms, meaning divide both sides by 4/3 pi, and make sure when you're typing it into your calculator, you divide it by 4/3 inside of parentheses, so that way it divides properly. And again, make sure pi is in your denominator and not on the side of your fraction. So I kept it as 8.65 divided by 4/3 pi. I didn't round that answer because when you divide this out, you're just left with r cubed. So you need a cube root both sides to get just r by itself. So I typed into my calculator the cube root of 8.65 divided by 4/3 pi, and that got me approximately 1.273 inches. So with that being said, thank you for watching these notes. I hope you learned something, and goodbye.